Hey gang, Terry here, and in this series we're going through the mathematical calculations, equations to calculate entropy, and we're going to stick to the thermodynamic definitions of entropy and use thermodynamics to go through that. And this is the very start of the series here, and we're going to start off with, how fitting, the thermodynamic definition of entropy, or also known as the Clausius definition of entropy. And I apologize to any German folks about my Canadian accent, but Rudolf Clausius, that's about as good as I can get there. So anyways, this is the thermodynamic definition of entropy here. This is the infinitesimal change in entropy. Entropy is abbreviated with the capital letter S. And in this definition, the infinitesimal change in entropy is greater than or equal to this infinitesimal change in energy as heat divided by the temperature. And we're going to elucidate why there's an equal sign and a greater than sign. At first glance, this might seem pretty annoying, but it does have some very deep underlying meanings behind it. Let's look at the equality sign first. So if this ds equals dq over t, this is true for a reversible process. Reversible process. And in a reversible process, the change in entropy is equal to the energy transferred as heat to the system. Now we can integrate this because these are infinitesimal changes here, and we can integrate it from some initial to final state here. And if we do that, entropy S is a state function. So the integral of ds is just the final entropy minus the initial entropy, and that is equal to just the change in entropy here, because S is a state function. It only depends on the final and the initial states. The change in entropy only depends on its final and initial state. It doesn't depend on the path and how we got there. Now this side is a little bit different because Q is a path function, so Q is path dependent. So we can't just say that this is equal to the change in Q over T. That doesn't work here. But if you imagine an infinitesimal amount of energy being transferred as heat to the system, and then we add up all of those infinitesimal heat transfers, we get the total energy that's been transferred as heat to the system. So this would be Q over T. So I'll put that over here. So this would be Q over T. And because there's an equality sign here, this equality sign means that this is a reversible process. So sometimes you'll see it with REV here, meaning this is only true for a reversible process here. Great. What about this inequality sign? Well, that's true for a irreversible process. Irreversible process. A reversible process is a hypothetical, idealized process. We never see a reversible process in real life. But every process that occurs in reality is actually irreversible. And in that case, the change in entropy, infinitesimal change, is greater than the energy transferred to it as heat. And if we integrate these here, initial and final state, here on the left-hand side, we still get the change in entropy greater than Q over T. And this is irreversible, an irreversible process. If every process that occurs in reality is irreversible, why do we even care about the reversible process, about this equality sign here, if we want to model reality? Well, the reason is that because entropy S is a state function, we can calculate the change in entropy between an initial and final state regardless of how we got there. So if we look at an irreversible process from some initial to final state, that change of entropy is equal to the same as the change of entropy for some reversible path to get there. So if we have some initial state here, we'll just call it I, which maybe is certain pressure, volume, temperature, that sort of thing. And then we have some final state here. And if we get from that initial state to the final state by some reversible process, some hypothetical reversible process, and we can calculate that hypothetically, we could also go from the initial state to the final state in reality, in this irreversible process. But by calculating the change in entropy between the final and the initial state, that change in entropy is the same regardless of if we got there reversibly or irreversibly. So that's why we care about this reversible, because thankfully entropy is a state function, so it helps us do that. Okay, now what about this one here? This looks like it's pretty much the same, and it is. This is the thermodynamic definition of entropy as well, with an equal sign, but this pertains to the surroundings. That's what SUR means, it's for the surroundings. Sometimes you might see SYS for the system, but if there's no subscript, then it implies that these variables pertain to the system here. So, and I should back up here. So for an irreversible system, this doesn't show up in the textbooks very often, but the temperature here is not the same. So is not for the system here. So for an irreversible process, this temperature is the temperature of the surroundings, or the heat reservoir that it comes from, the hot reservoir or the cold reservoir of it. Now in this case, for the surroundings is literally the rest of the universe. And the rest of the universe is so vast that there's essentially no volume change. The change in internal energy is equal to the energy supplied to it. Any loss in energy as heat from the surroundings goes directly in reducing its internal energy. So we have this direct relationship. We can go through it with exact differentials, but with the surroundings, just know that there's an equal sign here. This Q, this pertains to the energy transferred as heat to the system. So if we have the system here, some system, and we have the surroundings transferring energy as heat to the system, so we have heat going in, the system is gaining energy as heat, so there's positive heat transfer into the system, and the energy that's gained as heat by the system is lost by the surroundings. So the surroundings loses the energy, this energy goes into the system here. That's why it's negative. So what's lost to the surroundings is gained by the system, and vice versa. What's gained by the surroundings, the energy transferred as heat is gained by the surroundings, is lost to the system. That energy has to go somewhere, and it's just being transferred from the surroundings to the system, or from the system to the surroundings. All right, so there's these two equations. There's going to be many more equations that we're going to come up with. Now, the other one is with the second law of thermodynamics, one of the most important laws, I think, in all of science, where the total change in entropy is equal to the change in entropy of the system plus the change in entropy of the surroundings. And all of that has to be equal to or greater than 0. There's this, again, we're seeing this equal sign and inequality sign. Well, you might have guessed why we have this in equals or greater than sign, because for a reversible process, the equality sign applies. So the change in entropy of the system plus the change in entropy of the surroundings, infinitesimal change, not surrender, is equal to 0. But for an irreversible process, which is any real process, any process that actually occurs in real life, is greater than 0 here. So we have our thermodynamic definitions of entropy, where we have, this is dq over t, and for the surroundings, we have negative dq over t. Since the energy gained by the system is lost by the surroundings, this equals 0. Now in this case, ds is greater than dq over t. So we can't just say it's equal to dq over t. This is less than ds, because we have ds is greater than dq over t. So this is where the inequality sign comes in. This one is literally, this is equal to our dq, negative dq times t. This is the equality sign. But this one, we have the inequality sign here, which is why we have the inequality sign here. All right, so we got 3 equations in our tool belt to calculate entropy. There's going to be many more. Here's a practice question right here. And we have energy, 150 kilojoules, is transferred reversibly and isothermally. So let's stop here for a minute. So isothermally means T equals constant. And we're transferring it to a block of aluminum. Okay, so we got a block here, and it's aluminum. And what are we doing to it? We have energy is transferred as heat, so that's Q. Q is energy transferred as heat, and it's being transferred to the block of aluminum. So Q is 150 kilojoules here at 298 Kelvin, and it's isothermally, so T is constant, and it's also equal to 298 Kelvin. Now the temperature doesn't change, and we're transferring energy as heat to this block. So shouldn't it warm up? Shouldn't it get hotter? We could think of this block as so large, maybe it's a very large block, that 150 kilojoules just doesn't really increase the temperature to any measurable amount. It might be so small that we can't measure that if this is a large block. So we're going to calculate delta S, so the change in entropy of the system, change in entropy of the surroundings, and then the change in entropy total here. Now this is a reversible process. So our equation is, we start with the infinitesimal change in entropy equals dq of a reversible process over t. Integrate both sides from some initial to final state, so before and after this energy being transferred. And that's our delta S, change in entropy of the system, equals Q reversible over T. We can just plug this in. So the system is gaining 150 kilojoules. So that's it. That's how much energy as heat went into it. The temperature is 298 Kelvin. And we'll plug that into our calculator. 150 divided by 298 equals 0.503. 0.503 kilojoules per Kelvin, or we can write it in joules. Doesn't matter. Joules per Kelvin. It's kind of nicer to see this number, I think. So 503 joules per Kelvin, that's how much the entropy of the system changes. What about the surroundings? Well, it's equal to this negative Q of the system over T. And this is a reversible process as well. We don't really need to write it here because this pertains to the surroundings, but there we go. Negative 150 kilojoules over 298 Kelvin, and it's negative because the surroundings are losing energy. They're losing 150 kilojoules, so that negative means it's a loss of energy. And these are the same numbers here, so it's 0.503 kilojoules per Kelvin, or negative 0.503 kilojoules per Kelvin, which is equal to negative 503 joules per Kelvin. Okay, and then the change in entropy total of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. And that's going to equal 0. So it's 503 joules per Kelvin minus 503 joules per Kelvin. So for an irreversible process, an idealized hypothetical process here, it's 0. Now, in reality, this would be greater than 0 because the change in entropy of the system would be greater than 503 joules per Kelvin. All right, we introduced a couple equations for entropy. As you continue on this journey with me, we're going to go through many, many other calculations so that you become an entropy warrior by the end of this. Thanks everyone for watching, and I'll see you in the next video. Cheers.